So, good evening, everyone. We will start at 7:30 now. First, on behalf of IAPT DP Khandelwal Birth Centenary Celebration Committee, PK College Contai and Contai Science Academy, I extend a very warm welcome to each one of you. I specially welcome Dr. Ananda Dasgupta, Dr. Subhash Samanta, the convener DPK BCC committee, and all the wonderful participants for this third lecture of this series under the Dr. Khandelwal's birth centenary celebrations. We are really happy to have Dr. Ananda Dasgupta with us because he was not well, and it was very nice for us that he has joined us and he will be delivering a lecture today. Before I proceed, I call upon Dr. S.C. Samanta, convener DP Khandelwal Birth Centenary Celebration Committee, to say a few words about this program. Dr. Samanta, please. Samanta, sir.
Sorry. I
Yes.
welcome everybody in this lecture of the series for the series developed by Khandelwal Birth Centenary Committee for which will be useful for doing physics experiment using softwares. So this is the third lecture of the series. We have seen if augmented with the appropriate software, then a simple low-cost experiment becomes a precise experiment. We are organizing these lectures for paying homage to Dr. D.P. Khandelwal, founder of IAPT. His birth. Dr. well-known physics teachers. He is one of the tallest teachers who is comfortable with both theory and experiments. I heartily welcome to deliver his lecture. Also welcome everybody, every student in this lecture. Thank you.
Thank you, sir. Now it's time to introduce today's guest speaker, Dr. Ananda Dasgupta. We are really happy to have him here with us today. Dr. Ananda Dasgupta is an associate professor in the Department of Physical Sciences of IISER, Kolkata. He obtained his PhD degree in physics from Jadavpur University in 2001. Formerly, he was in St. Xavier's College, Kolkata and Jadavpur University. His research interests encompasses algebraic techniques in the field of quantum optics, especially in squeezed states and matter radiation interaction. He is especially interested in the fundamental quantum mechanical and statistical issues involved. He has published a good number of quality research articles in various internationally acclaimed journals. So let us welcome him again, and we are really eager to hear Dr. Ananda Dasgupta. So over to you, Dr. Ananda Dasgupta. Once again, a very warm welcome to you from all of us.
Thank you, Dr. Ghorpade, for this kind introduction. And I must thank the Contai Science Academy and the PK College Contai for giving us this, bringing this wonderful workshop for us and giving me a chance. But I'm not really sure whether I should also thank IAPT for the simple reason that I have been a part of IAPT myself for so long that this sounds very much like thanking myself. So, okay, I will not formally thank the IAPT simply because it's something almost like a second home to me by now. Okay, let me just start my presentation first. And of course, you have to tell me whether the presentation is visible. And I must
visible,
no, let's just check.
You are visible.
So I have started presenting my screen, and the presentation should be on your screen now.
Yes, sir. Yes, it is visible.
Okay?
It's visible.
Yes.
Okay. So thanks for confirming that. Let me just check one thing. I should actually hide the button. Stop presenting, ignore, there's no. Okay, fine. I think that's. Okay. Now, at the very outset, let me confess that I am a bit intimidated as well as thrilled to be giving this lecture for several reasons, not the least of them being that this particular workshop is a part of the celebration of the centenary of a wonderful physicist, Professor Khandelwal, and especially one of the doyens of experimental physics, especially experimental physics at the level of pedagogical teaching in India. And frankly, I belong to the group of people whom our instructor or our teacher at Shah Institute of Nuclear Physics, who used to be our teacher for experiments, used to derisively call the Shy Star Shy Gang. So we are really theoreticians. So frankly, I'm not very sure whether I'm very well qualified to be delivering a talk here. But I've dappled with experiments simply because I've been a college teacher for a large part of my life, and even now I am an undergraduate teacher as well. So I have had to do experiments and thought a bit about them. So I will share some of that with you. I'm pretty sure there are many here who are actually much better versed in experiments than I am. And of course, I must apologize to all of you for the delay in this lecture. This was scheduled a long time ago. But nowadays, this old proverb, man proposes, God disposes, has changed to man proposes, COVID disposes. So thankfully, I'm in a position to sort of give you a lecture by now. And I hope it will not be too much of a boring thing for you to have to hear. Basically, the ramblings of a theoretical physicist on what kind of things, experiments can be done at home with using little software and so on. So let me begin with the background of the kind of experiment that I'm going to talk about. I'm essentially going to talk about the use of sound to do mechanical experiments. And I will explain the particular experiment that I want to talk about here. But there are many other possible experiments that you can do by using this basic principle. So I will just leave that to your imagination. We will start with the basic physics here, and this is of course familiar to everybody in the audience. This is basically class 11 stuff. If you have a bouncing ball which is dropped on a hard table or the floor, of course it bounces. Now the picture here is one I took from the internet. It's slightly misleading in the sense that we are not really making the ball drop parabolically. That is, we are not giving it's an angle. We are going to try to drop it as vertically as possible. So it's going to just go up and down. Of course, this is a stop motion picture made out of many, many pictures of a bouncing basketball. And they had to drop it at a slight angle, simply so that the balls would not overlap with each other completely. But in practice, we will try to do this as vertically as possible. Now, as you all know, every time it bounces, the bounce is not perfectly elastic, this collision. So there is something called the coefficient of restitution which comes into play. And since the ball is reflecting from a fixed platform, either the table or the floor, the velocity of the ball immediately after the collision gets reduced compared to the velocity immediately before by this simple relationship, Vn plus 1 equals R times Vn, where R, this number, is smaller than 1 and it's the coefficient of restitution. And this, of course, was first proposed by none other than Isaac Newton, who did a series of experiments also to verify that this really works out. And since the speed is going down on every bounce, the bounces get progressively closer together in time. Of course, the ball rises less and the bounces also get closer together. So our aim essentially is to, in this experiment that I'm going to describe, is to try to understand this particular phenomenon as well as, and try to explore this and use it to measure or determine some parameters which can be checked against other experiments as well. In particular, what we are going to try to do is determine the coefficient of restitution itself, as well as determine the value of g, the acceleration due to gravity, using the bouncing ball. Now, before I go on to talk about the software version, where we use slightly more advanced stuff to do the experiment, the actual experiment. Let me try to describe how I would have approached this experiment if I did not have any software available. And just before that, I would like to talk a bit about the basic maths involved here, but these are formulae which all of you are definitely familiar with. Some of you may have forgotten. This is so elementary, so I'm just going to give you a brief recap of this. So if a ball is dropped from a height of small h, when it hits the ground, of course, its speed is root over 2gh. We are assuming that the ball is being dropped from a small enough distance that we can ignore the air resistance and stuff like that. So the velocity with which it hits the ground is root over 2gh. Now, since the velocity gets reduced by a factor of r, or rather gets multiplied by a factor of r, every time the bounce occurs, the speed right after the nth bounce is given by Vn, which is r to the n times V0. And from elementary mechanics, again, class 11 stuff, even perhaps class 10 stuff, time interval between the nth and the n plus 1th bounce, where we are starting with a velocity of r to the n V0, Vn, is simply given by twice Vn by g. Once again, we are assuming that air resistance can be ignored here, which is a decent approximation as long as you are not dropping it from too great a height. So Tn, the time interval between the nth and the n plus 1th bounce, is just twice V0 by g times r to the n. And the problem is this time interval is actually pretty small for a ball which has been dropped from a small height, let's say 30 centimeters or 40 centimeters, or even less. 10 centimeters might be a decent amount for this. This particular TNs are actually quite small. So they would be very difficult to measure using standard equipment. So what we can do is what we always do. Instead of measuring one oscillation of pendulum, we usually measure several, right? And then, of course, with the pendulum, we know that each oscillation should take the same amount of time. So we estimate the time period by dividing the total time that we determine by the number of oscillations. Here, of course, we can't do that because the time intervals are actually decreasing. But we can easily calculate that between the first bounce and the nth. Of course, when I say nth, that's the nth bounce. That means it's the bounce which starts at the n minus 1th bounce and goes up to the nth. So you have to add up these interval tn's from n equal to 1 to n equal to capital N minus 1. So these are the n minus 1 intervals between the first bounce and the nth bounce. And if you just do the summation, this is trivial. This is a geometric progression which can be summed up trivially. And you end up with this final result. It's root over 8h by g times r minus r to the n by 1 minus r. So if you can determine Tn, from this formula you can easily see that if you drop the ball from a particular height h, which you have measured beforehand, and you know the acceleration due to gravity in your locality, then by counting of sufficiently large number of bounces for a large n, if you measure Tn, that is the time it takes for the ball to bounce first time around and then till the nth bounce, then we can determine this quantity r